So the roots S12 are negative zeta omega n plus minus omega n square root of zeta squared minus 1. And let's expect the roots and the response for each value of zeta. So for zeta greater than 1 or over damped systems, the value here is positive and the roots will remain real. And when your roots are real, remember that we started with x of t equals some amplitude e to the power st. I have two values for s and both are reals values, so the response will be some constant a e to the power the first root, which is negative zeta omega n plus omega n square root of zeta squared minus 1 all times t plus some constant b e to the power negative zeta omega n minus square root of zeta squared minus 1 all times t. Now, a and b constants are determined by the initial conditions. We will have two initial conditions in the system, x of 0 and x dot of 0. So a and b are determined by initial conditions. Now, notice that when zeta is greater than 1, this term is always smaller than this term, because when zeta is 1, or this term will be 0. For greater than 1, the term will start growing, but it will always be less than negative zeta omega n, which means both roots will always be negative roots. So for zeta greater than 1, both roots are negative. So I will have e to the power a negative value in both cases. So if I look at the response x of t as a function of time t, then if I have some initial conditions at this point, the function e to power negative value is an exponential function decaying with time, approaches 0 at infinity. Now, how fast this function approaches 0 depends on the value of zeta. As zeta grows, this part of the root, this root will become more and more negative, and the response e to larger negative number will approach 0 a little faster. So for these curves, you can say that zeta is greater than 1. And this is what the response will look like. It will decay to 0 as time goes by. Now, what about the case when zeta is equal to 1, which is a critically damped system? The roots S1, 2 will be negative zeta omega n, and we said we will have a double root. Both S1 and S2 are zeta omega n. In this case, x of t will be some amplitude e to the power negative omega n t, this is the first root, plus b e to the power negative zeta omega n t. But because we have double root, I will have to multiply this by t. Can simplify it as a plus b t e to the power negative zeta omega n t. Now, this term right here grows with time, goes to infinity as time goes to infinity. But as time grows, also this term goes to approaches 0. E to negative value will approach 0, and this will approach infinity. But since this approaches infinity linearly, this is a linear function, and this approaches 0 exponentially, which is much faster than the linear function, the multiplication will end up being going to 0, and the response will look like, will also approach 0. That's for zeta equals 1. The system is critically damped. So again, we have sort of exponential response decaying with time. Finally, what about the case when zeta is less than 1? That's when the system is under damped. Now, the roots S12 are negative zeta omega n plus minus omega n square root of zeta squared minus 1. But since zeta is less than 1, this is going to be negative. A negative square root will end up being an imaginary term. So I can rewrite this as negative zeta omega n t, omega n, sorry, plus minus. I'll take the negative, I'll multiply this by negative 1 and take the square root of negative 1, which is I omega n. Now, 1 minus zeta squared. Now when it's 1 minus zeta squared, and zeta is less than 1, this is positive, which we can find the square root for, and I have the complex index here, so the roots are complex roots. And the response x of t will be x of t to be x e to the power, the first root is negative zeta omega n t plus I omega n square root of 1 minus zeta squared, all multiplied by t, and plus e to the power negative zeta omega n t minus I omega n square root of 1 minus zeta squared multiplied by t. Now I can take the exponent, the exponential function e to the power negative zeta omega n as a common, e to negative zeta omega n t x e to the power I omega n square root of 1 minus zeta squared t plus x e to the power negative I omega n t square root of 1 minus zeta squared t. Now recall that when we have an exponential function with a complex index or imaginary term, recall that sine of theta is 1 over 2j over I in this case times e to the power I theta minus e to the power negative I theta, and cosine theta is 1 over 2 e to the power I theta plus e to negative I theta, which means I have here the same thing. If I consider this as theta, then I can convert or change these two exponential functions, exchanging by theta, sine theta, and cosine theta. I can remove these two terms and represent them as a combination of sine and cosine functions as follows.